Welcome to this explainer. Today we're unpacking a really fascinating scientific mystery in the AI world. We're looking at a paper that takes a pretty major failure and turns it into a massive success. It's all about recent research detailing a system called QuTrim. But, this isn't just a story about some shiny new AI tool. It's actually a masterclass in how researchers diagnose a problem when their model falls completely flat on its face, and how they engineer a brilliant, highly targeted fix.
So, let's just dive right into the immediate stakes here. Modern large language models have absolutely staggering computational costs. As our context windows keep stretching longer and longer, the sheer volume of tokens processed at inference time makes running these models incredibly expensive. We desperately need to figure out a way to bring those costs down without breaking the model's accuracy.
The solution a lot of researchers are chasing right now is something called token pruning. Think of it kind of like a ruthless book editor, cutting unnecessary filler words from a manuscript, but without losing the core plot. Token pruning drops unneeded data, basically tokens the model is least likely to actually need for the math later on, so the AI just runs faster and cheaper. If you can accurately predict which tokens don't matter, well, you just skip processing them entirely.
Part 1. Enter QuTrim. To tackle this inference problem, researchers introduced QuTrim. It was designed to act exactly like that ruthless, highly efficient editor. And the pipeline is actually really elegant. It takes the input token sequence, shrinks the data down using PCA dimensionality reduction, and then finally scores each token using a variational quantum circuit. That score decides how important a token is to keep. Now, before we go any further, we really need to clarify exactly what quantum means in this context, and we'll use the author's own very transparent disclaimer here to build some trust. This is a quantum-inspired mathematical approach running entirely on standard classical hardware. We are not talking about sci-fi machinery or massive cryogenic quantum computers. The researchers explicitly state they are making absolutely zero claims of computational speedup from quantum effects. They're literally just using the mathematical structure of a quantum circuit as a novel way to score these tokens.
Moving on to Part 2, the initial failure.
This is where our scientific mystery really kicks off, because QuTrim's very first iteration was an absolute, undeniable failure. When they tested it by looking only at the contents of the tokens, it lost to almost every single classical baseline. It lost to a standard parameter-matched classical neural network. It lost to a simple heuristic. But most painfully, it lost to literal random pruning in 5 out of 6 test ratios. Just imagine building this complex, quantum-inspired score, only to find out that closing your eyes and picking tokens at random works better. For a lot of teams, that would have been a total dead end.
But they didn't just give up. They ran an ablation study to see if maybe their quantum circuit was simply too small. And when you look at the data mapping circuit size against pruning quality, where, by the way, lower perplexity is better, there is no clear downward trend at all. In fact, the absolute smallest configuration, with just 6 trainable parameters, actually beat the 48-parameter one they were initially using. That definitively proved the circuit was large enough. It was just learning completely the wrong things.
Which leads us to Part 3, the positional fix.
This sparked a massive aha moment in the diagnosis. The researchers realized that the one baseline beating everyone else was using positional information. QuTrim only knew what the words were, not where they were. So the brilliant fix was incredibly simple. Alongside the content, they just added the normalized distance from the beginning and the end of the sequence right into QuTrim's input. And just to keep the comparison perfectly fair, they applied this exact same fix to the classical baseline too.
This next finding brilliantly illustrates the weird nature of machine learning. When examining the training curves with this new positional fix, the classical model fits the proxy training target much tighter, dropping to a significantly lower loss than QuTrim. You'd naturally assume that makes it better at pruning, right? But fitting a proxy target tightly doesn't actually guarantee better downstream pruning quality. It's a bit of a trap.
Just by adding those 2 tiny positional features, the rate of catastrophically wrong pruning outcomes dropped to 30.5%. Now, while that's still a bit high, it was a massive improvement from the initial content-only version. It proved that positional awareness provided a much more stable signal. The model wasn't just randomly throwing away crucial structural tokens anymore.
Bringing us to Part 4, long context success.
The real proof of concept arrived during the long context evaluation. This is a highly realistic scenario where only the context is pruned and the AI is tested on generating a continuation. Honestly, this is exactly how you'd use token pruning in the real world to save money on massive prompts. When plotting the perplexity on a log scale, QuTrim and the absolute strongest baseline are practically overlapping at the very bottom, miles and miles ahead of random pruning.
And the numbers absolutely confirm the turnaround. With the positional fix, QuTrim significantly outperformed both the classical model and random pruning across all 6 pruning ratios tested. Remember, before the fix, it was losing to random guessing. Now, it's statistically indistinguishable from the absolute strongest training-free positional heuristic out there. Talk about a comeback.
So the really crucial takeaway here is that transparently diagnosing a failure and applying a targeted fair fix resulted in a compact, position-aware tool that completely matches the strongest baselines. The researchers didn't hide their initial negative result. Instead, they used it to form a specific hypothesis that they were missing positional data, tested it minimally, and turned a total dead end into an actionable, highly competitive solution for LLM efficiency.
I'm going to leave you with this final thought. Given how incredibly powerful this simple 2-feature positional fix was, and considering that proxy training loss doesn't always equal pruning quality, imagine the massive efficiency gains we might unlock when we optimize this directly for downstream generation. Like, what happens when we train these position-aware scores entirely end-to-end? The future of making massive AI cheaper to run might just rely on knowing exactly where you stand.